Hello and welcome to today's video on advanced hypothesis testing and introduction to regression. In this video, we will talk a bit more about hypothesis testing. Then we will give a brief introduction to regression, basically linear regression and logistic regression. And as usual, this video will be followed by another walkthrough in R. To continue on our discussion on hypothesis testing from the last video, let me introduce you to what is known as matched pair t-test. Often there is a requirement to compare before and after. So for example, if you have a segment of customer who spend, let's say, $100 per month in your shop, then you decided to launch an offer targeted specifically towards that segment. And you notice that the amount has increased to 110. If you want to understand whether there has been a significant change in the average amount of money this same segment of customers spends in your shop, that is when you use matched pair t-test. So there is a situation before something and then after something, and you want to compare this before and after. Another example could be, let's say, performance of employees before and after a training, or maybe the level of cholesterol before and after taking a medicine. Or maybe how about, let's say, GDP before and after a policy. Another type of hypothesis testing is called Chisquared tests. It is used when you want to understand if there is any independence of association. So for example, you have several types of visitors on your website and you have categorized some of them as teenagers. You want to understand whether there is an association between this segment and your website. That is, whether this segment prefers your website more than the others. It is also useful in identifying equality of proportions. So let's say, is your customer satisfaction equal across different states, different geographies, different product segments? Similarly, it can also be used to identify goodness of fit, that is, whether a data is normally distributed or not, for example. Now, both of these matched pair t-tests and chi-square tests, we will show how it is done in R. The next one is called analysis of variance. So till now we have spoken about two populations. We were basically comparing parameters of two populations. What if there are more than two populations? That is where ANOVA comes into picture. So for example, does the average fuel consumption vary across 5 different makes of particular HPF tractors? Or does the fuel consumption vary across, let's say, particular engine cc automobiles, and so on. So there you want to compare the average fuel consumption of more than two populations, and that is where you use analysis of variance or ANOVA. In this case, the hypothesis, the null hypothesis becomes as shown here: mu1, mu2, mu3, are they equal or not? Are they equal or not? Mu means mean. And similarly, the alternative hypothesis is at least one of these mu I 1, 2, 3, at least one of these is different from the other two. At least all of the three can be different, but at least one of them is different. Again, this the way it is done in R will be shown in the walkthrough video. So before moving on to linear regression, let me try to reinforce the understanding or the concept of hypothesis testing using normal distribution. So when we talk about normal distribution, it can take various forms. Let's say this one, this one, this one, this one. All of them are normally distributed, but they still have different geometry, different parameters, different shape, different height, and so on. Now from statistics, we know there are established formula to estimate this spread or estimate this geometry or estimate this height depending on availability of certain information. Now let's say we have a sample with a mean of x. So when we have a sample mean of x from a random sample taken from a normally distributed population, we know that the population mean will be normally distributed like this, for example. Now we want to understand whether this particular sample mean falls anywhere under this actual population mean. How do we do that? So we have established formulas which provides us something called Z-crit or T-crit or F-crit, depending on the information available and the distribution under consideration. Different names are used, but basically they indicate the position on the x-axis. So for example, you want to understand whether this x falls under, whether this x is a possible mean of the population, whether this x is a possible mean of the population, and you want to do that with, let's say, 95% confidence interval. That is, you want to have a level of significance or alpha of 5%. Now when you want to do that, the 5% is divided into two parts, one in this part, the other in this part. So this is 2.5% and this is 2.5%, right? Now you want to understand whether this x falls within this range. If you want to understand whether x falls within this range, let me try another color, within this range. Now when you have certain information about the sample, you can estimate these values, let's say Z, F-crit, T-crit or F-crit. And what do they give? They give the corresponding position. So for 95% confidence interval, that is 2.5% from here, if you come towards the center, then it gives us, let's say, in our case, let's say Z-crit. So this is Z-crit value of one of them. Let's say it is equal to A, and then this one is equal to, let's say, A dash, right? So from this value, from confidence interval or from the level of significance or alpha, we find the statistic of this particular position. So 95th percentile here, and then 2.5 percentile here. What is the value of the corresponding statistic? Once we have that, we convert this sample mean into this kind of statistic like Z-stat or T-stat or F-stat. So in the first step, with the level of significance or the confidence interval, we mark the value of the points. So 95% is between this point and this point. And then what we do is we use this particular sample mean and convert it into the terms of Z, T or F, and then we find out. So let's say in our case this X translates into a value B which falls somewhere here. So if this B falls between these two, let's say Z-crit values, then we can say that this is a possible mean of the population, right? To repeat, Using the level of significance or the confidence interval, we first of all calculate the limit or the Z crate or F crate or T crate values in the distribution and define particular points. And depending on the hypothesis, we sometimes use 2 points and sometimes use 1 point. You can remember the two-tailed and one-tailed test. And then the sample parameter is translated into this Z number or Z stat or F stat or T stat. And then you compare whether that particular F stat, Z stat or T stat is in between the Z crate, F crate or T crate, or let's say in certain cases less than or more than Z crate, F crate or T crate. Now let us talk about linear regression. What is linear regression? Linear regression tells us, let's say, about the strength of relationship between variables. So if we have two variables here, let's say one in x-axis, one in y-axis, we want to understand the strength of the relationship between these two variables. It is better described in the following manner. So what will make things extremely simple to predict, and in general very simple? So usually if there is a company, they manufacture a product, you can, and if they sell, let's say 10 items every month irrespective of anything, that is, you can predict each and everything, and every month irrespective of anything they are selling 10 items. That is a scenario, let's say. Now in real life that never happens. Sometimes it is 10, sometimes it can be 9, sometimes it can be 8, sometimes it can be 15, and so on. So what does it mean? It varies, right? So it has a mean and there is a variance. There is a variance from the mean. So if the mean is, say, let's say A, then there is a variance in the values. Let's say sales here. Now what is causing this variance? Why is sometimes sales high and sometimes low? One of the parameters could be marketing budget. So let's say marketing budget. And you want to understand how much of the variance is being caused by this marketing budget. So let's say the sales should have been, or the mean sales is, let's say 10, and every month it is selling, it could have sold 10. However, there is a variance. Sometimes 9, sometimes 8, sometimes 15, sometimes more, and so on. So what is causing this variance? There could be several factors, but one of them is marketing budget. And we want to understand how much of this variance is actually caused by this marketing budget. That is when we use linear regression to understand how much of the variance is caused by one variable on another. So we say that one is dependent variable. Let's say in our case the sales is a dependent variable and the other is called independent variable. Let's say marketing budget, which is independent variable. And to do that, what we do is we try to find out a relationship, and one of the way is assuming that there is a linear relationship. If you go back to algebra, you will know that this is a very familiar formula of lines, linear equation. So what happens is that we assume that these two variables, let's say sales and marketing data, they are linearly related. That is, we assume some value of beta 0, beta 1, and then we draw different lines. Let's say this is another line, this is another line, and when we draw that line, we try to understand what is the distance of this particular line from the actual value. So what is the distance of the original points from this line? Okay, and the line with which the sum of all these distances is the minimum, that is the line we call as, we consider that line to be the optimum line to predict the dependent variable using independent variable. So even if, let's say, we use this particular line, this red line, using a value of x, that is the marketing value, we would have obtained a value of sales, right? Because x, y. Similarly, if we used another line, we could have predicted a value of y from x, that is predicted a value from marketing budget. However, out of all these lines, one will be the most optimum, one will be most accurate, one that has the least amount of error, and that error is measured by the distance of the original point from these lines. So let's say you have drawn multiple lines and you found one line which has the least amount of error, that is the sum of the distance of these points from this line is the least, and that is the most optimum line, and that is the one that is used in the actual equation. We will see how it is done in the walkthrough video. Now, similar to linear regression, we have something called logistic regression. In linear regression, we predict an amount or predict a number. There are some other kind of problems where you don't predict number, rather you predict whether or not, or you classify something as yes or no, or into different groups. And one such is, for example, here you want to understand yes and no question. For example, in this case, credit card failure or credit card default based on the balance in the credit card. So let's say you have balance shown here in the x-axis, and the probability of default is shown in y-axis. Now here also we could have used the linear regression. However, when you use linear regression as shown here, sometimes the probabilities go below 0, which does not make sense. To solve this problem, we use logistic regression. The linear regression is transformed using logarithm, and then this kind of shape is obtained, which guarantees that the range of outcome or range of prediction is always between 0 and 1, both included, and that is when we use logistic regression. To repeat, linear regression helps us understand how some of the variables are affecting the variance of another variable. In plain words, it helps us predict. Using linear equation, we assume a linear relationship and we want to try to predict things. That is what is linear regression. And a slightly different version of linear regression is logistic regression, where classification is involved, where we don't have to measure certain value, or we don't have to predict certain value, or we have to identify whether or not something has happened, or we want to classify something yes or no, or predict the probabilities of happening something yes or no. Well, that brings us to the end of this video. I hope you enjoyed this. Please feel free to give your feedback in the comments, or you can approach me with any of the doubts that you may have. I would really appreciate your support in form of likes, shares, and subscription. Thank you very much.